Before we descend into the darkness, I want to ask a favour. If you enjoy this story, please use your hype points on this video. It helps the channel more than you possibly know. If you're listening on Spotify, leaving a review makes a massive difference. And if you'd like, comment what time it is and where in the world you're listening from. We absolutely love seeing where everyone is tuning in. And of course, if you enjoy the content, consider subscribing. Now let's begin. Let's begin with a simple common sense principle about how we gather evidence in the world. If you want to learn something about ravens, those large glossy black birds you might see perched on fence posts or circling overhead, the natural thing to do is to go out and look at ravens. If someone claims that all ravens are black, you would probably test this claim by observing as many ravens as you could find, checking their colour and seeing if the pattern holds. This feels right. It feels obvious. When you want to confirm or disconfirm a statement about a particular kind of thing, you examine instances of that thing. You look at the subject of your inquiry directly. You don't wander off to study something entirely different. If you're investigating ravens, you study ravens. If you're investigating swans, you study swans. If you're investigating electrons, you study electrons. The evidence that matters is the evidence that comes from the thing you're actually talking about. This intuition runs deep in how we think about science and evidence. It's part of what makes empirical investigation feel grounded and sensible. When a biologist wants to understand the behaviour of a particular species, she goes into the field and observes that species. When a chemist wants to understand the properties of a particular compound, he works with that compound in the laboratory. The directness of this approach seems like a fundamental virtue. It keeps us honest. It keeps us focused. It prevents us from getting lost in abstraction or irrelevance. If you're making a claim about X, you should be looking at X to test that claim. This is the bedrock intuition underlying much of our everyday reasoning about evidence and confirmation. But there exists a puzzle in philosophy, a strange little thought experiment that takes this bedrock intuition and shakes it gently until it starts to feel unstable. This puzzle is known as the Raven paradox, and it was first articulated by the philosopher Carl Hempel in the middle of the 20th century. Hempel wasn't trying to overthrow science or suggest that evidence doesn't work. He was doing something more subtle and more interesting. He was pointing out a tension between different ideas we hold about confirmation, a tension that becomes visible when you follow the rules of logic very carefully and see where they lead. The Raven paradox doesn't tell us that science is broken. It tells us that our intuitive concept of evidence is more complicated than it first appears, and that when we try to make that concept precise, we run into some genuinely strange implications. The paradox centres on a very simple claim: all ravens are black. This is the kind of statement you might find in a field guide or hear from someone who has spent time watching birds. It's a universal generalisation, a claim about an entire category. It says that if you find a raven anywhere in the world, that raven will be black. Now, if you wanted to test this claim, what would you do? You would go out and look at ravens. Every time you saw a raven and confirmed that it was indeed black, you would feel that you'd gathered a small piece of evidence in favour of the claim. Every black raven you observed would seem to support the hypothesis. And if you ever found a raven that wasn't black, a white raven, a brown raven, a green raven, you would have disproven the claim immediately. That's how universal generalizations work. They're vulnerable to counterexamples. A single non-black raven would be enough to show that the claim all ravens are black is false. So far, everything makes sense. The confirmation process feels straightforward. But Hempel noticed something peculiar when he started thinking about the logical structure of the claim all ravens are black. He realized that this claim can be rephrased in a way that is logically equivalent, but sounds very different. The original claim says that all ravens are black. The rephrased version says that all non-black things are non-ravens. Take a moment to let that sink in. These two statements, despite sounding different, are saying exactly the same thing from a logical point of view. They rule out the same kind of counterexample. They describe the same constraint on the world. To see why these statements are equivalent, think about what would violate each one. The first statement, all ravens are black, is violated if you find something that is a raven and is not black. The second statement, all non-black things are non-ravens, is violated if you find something that is non-black and is a raven. But notice, these are the same violation. A non-black raven would contradict both statements, and nothing else would contradict either statement. If you found a black raven, that wouldn't violate all ravens are black, and it wouldn't violate all non-black things are non-ravens either, because a black raven isn't a non-black thing. If you found a green apple, that wouldn't violate all ravens are black, because the apple isn't a raven, and it wouldn't violate all non-black things are non-ravens, because the apple is indeed non-black and indeed not a raven, which is exactly what the second statement predicts. The logical equivalence here is airtight. If one of these statements is true, the other must be true. If one is false, the other must be false. They cannot differ in truth value. They are two ways of expressing the same fact about the world. This is not controversial from a logical standpoint. It's a basic application of contrapositive reasoning, a principle that has been understood since ancient times. If A implies B is true, then not B implies not A must also be true. In this case, being a raven implies being black is equivalent to being non-black implies being a non-raven. The logic is clean and clear, but here is where the paradox begins to emerge. If these two statements are logically equivalent, then it seems like they should be confirmed by the same evidence. This is a principle that Hempel called the equivalence condition. If two hypotheses are logically equivalent, then any evidence that confirms one should also confirm the other. This principle also seems reasonable. After all, if two statements are just different ways of saying the same thing, then learning something that supports one of them should support the other as well. Evidence shouldn't care about how you phrase your hypothesis. If you have good reason to believe that all ravens are black, you should have equally good reason to believe that all non-black things are non-ravens, because these are the same claim. Now let's think about what would confirm the second version of the hypothesis, the one that says all non-black things are non-ravens. To test this claim, you would examine non-black things and check whether they are ravens or not. Imagine you're sitting in a room and you look around. You see a green apple on the table. The apple is non-black, and the apple is not a raven. So the apple is consistent with the hypothesis that all non-black things are non-ravens. In fact, the apple seems to confirm that hypothesis in the same way that a black raven confirms the hypothesis that all ravens are black. You found an instance of a non-black thing, checked it, and verified that it is indeed not a raven. That's one more piece of evidence in favour of the claim. But wait, if observing a green apple confirms the hypothesis all non-black things are non-ravens, and if that hypothesis is logically equivalent to all ravens are black, then by the equivalence condition, observing a green apple should also confirm the hypothesis all ravens are black. And this is where the feeling of paradox arrives in full force. It seems bizarre to say that looking at a green apple, an object that has nothing to do with ravens, that you might find in your kitchen or at a grocery store, could provide evidence about the colour of ravens. It feels wrong. It feels like a trick. If green apples confirm that all ravens are black, then so do blue cars, red shirts, white walls, and every other non-black thing in the universe that isn't a raven. You could sit in your living room, never venturing outside, never seeing a single raven, and yet accumulate evidence about ravens just by glancing at the objects around you. This is the raven paradox in its full strange glory. On one hand, the logic seems impeccable. The two hypotheses are equivalent, so they should be confirmed by the same evidence. Observing a non-black non-raven is evidence for all non-black things are non-ravens, and therefore evidence for all ravens are black. On the other hand, the conclusion feels absurd. Surely a green apple tells us nothing useful about ravens. Surely confirmation doesn't work this way. We're left with a tension between logical principles that seem correct and intuitions that feel equally strong. Something has to give, but it's not immediately clear what. Let's linger for a moment on why this feels so absurd. Part of the discomfort comes from the sheer abundance of non-black non-ravens in the world. Think about how many things exist that are neither black nor ravens. There are green apples and red apples and yellow bananas and orange oranges. There are white clouds and blue skies and grey stones and brown dirt. There are purple flowers and pink shirts and silver spoons and golden rings. The category of non-black non-ravens is vast, almost unimaginably large. If each of these things counts as confirming evidence for all ravens are black, then the hypothesis would seem to be supported by an overwhelming mountain of observations, even though we haven't looked at a single raven. Meanwhile, the category of ravens is quite small by comparison. Ravens are a specific species of bird, and while they're not exactly rare, they're certainly much less numerous than non-black non-ravens. If you wanted to find ravens to study, you'd have to go to places where ravens live, and you'd have to spend time looking for them. You might see a few ravens in a day, or a few dozen if you're lucky and persistent, but you can see thousands of non-black non-ravens just by walking down the street or sitting in your home. The asymmetry is striking. It seems like the hypothesis all ravens are black would become confirmed far more easily by observations that have nothing to do with ravens than by observations of ravens themselves. And that seems backwards. That seems to violate the basic principle that evidence should be connected to the subject matter of your claim. There's another layer to the absurdity as well. When you observe a black raven, you feel like you're taking a genuine risk. You're looking at something that could, in principle, falsify the hypothesis. If the raven turned out to be non-black, the hypothesis would be refuted, so observing a black raven and finding it to be black feels like a meaningful test. You put the hypothesis in jeopardy, and it survived. But when you observe a green apple, there's no sense of risk. You're not worried that the apple might turn out to be a raven. You know, before you even look closely, that the apple is not a raven. So in what sense are you testing the hypothesis? In what sense are you gathering evidence? The observation feels uninformative, precisely because the outcome was never in doubt. This is the heart of the paradox. We have a conflict between different principles we hold about evidence and confirmation. On one side, we have the equivalence condition. Logically, equivalent hypotheses should be confirmed by the same evidence. This principle seems to be grounded in basic logic and rationality. On the other side, we have the intuition that evidence should be relevant to the claim being tested, that you should examine instances of the thing you're talking about, that confirmation shouldn't come from observations that are obviously uninformative. This intuition seems to be grounded in common sense and scientific practice. Both principles feel compelling, but they pull in opposite directions when we think about ravens and green apples. So what exactly is the paradox showing us? It's important to be clear about this. The paradox is not showing us that logic is broken. The logical equivalence between all ravens are black and all non-black things are non-ravens is genuine and unproblematic. The paradox is also not showing us that we can learn about ravens by looking at apples in any practical sense. No ornithologist would study apples to learn about bird coloration, and for good reason. What the paradox is showing us is that our intuitive concept of confirmation, the idea that evidence supports or strengthens a hypothesis, is more subtle and more complicated than we might have realised. When we try to articulate rules for confirmation that seem simple and obvious, those rules can lead to conclusions that clash with our intuitions. The raven paradox is a signal that we need to think more carefully about what confirmation means and how it works. Let's explore one way of resolving the paradox, an approach that has been very influential in philosophy of science. This approach says that we should take seriously the idea that observing a green apple really does confirm the hypothesis all ravens are black, but that the amount of confirmation provided is so tiny, so negligible, that it doesn't matter in practice. In other words, yes, the apple confirms the hypothesis, but only by an infinitesimal amount, far too small to make any real difference to our beliefs or our scientific conclusions. This approach tries to reconcile the logical arguments with our intuitions by distinguishing between confirmation in principle and confirmation in practice. To understand this resolution, we need to think about confirmation in a more quantitative way. Not all confirming observations are created equal. Some pieces of evidence provide strong support for a hypothesis, while others provide weak support. When you observe a black raven, you're providing relatively strong support for all ravens are black, because you're directly testing the hypothesis by examining an instance of the subject matter. When you observe a green apple, you're providing extremely weak support, because you're examining something that was already almost certain not to be a counterexample. Both observations confirm the hypothesis in some sense, but the degree of confirmation is vastly different. Think about it this way. The hypothesis, all ravens are black, is vulnerable to a specific kind of counterexample, a non-black raven. When you observe a raven and find that it's black, you've ruled out the possibility that this particular raven is a counterexample. That's meaningful, because before you looked, there was some chance, however small, that this raven might not be black. When you observe a green apple, you've also ruled out a possibility, the possibility that this particular green apple is a non-black raven. But that possibility was never plausible to begin with. You knew, before you looked closely at the apple, that it wasn't a raven. So the observation doesn't really change your state of knowledge. It confirms the hypothesis only in the most technical, trivial sense. This way of thinking about confirmation is closely related to Bayesian approaches to evidence and probability. In Bayesian reasoning, evidence is said to confirm a hypothesis if it increases the probability of that hypothesis being true. The amount of confirmation depends on how much the probability increases. If you start with some prior probability that all ravens are black, and then you observe a black raven, the probability increases by some amount. If you observe a green apple, the probability also increases, but by a much, much smaller amount, so small that it's effectively zero for practical purposes. Why is the confirmation from the apple so small? It comes down to base rates and background knowledge. Before you make any observations, you already have a lot of knowledge about the world. You know that ravens are birds. You know that apples are fruits. You know that birds and fruits are different kinds of things with different properties. You know that the category of non-black things is enormous, and that the category of ravens is tiny by comparison. When you randomly select a non-black thing to examine, the probability that it's a raven is already vanishingly small, almost regardless of whether the hypothesis all ravens are black is true or false. So when you observe that the non-black thing is not a raven, you're confirming something you were already almost certain of. You're not learning much. By contrast, when you specifically seek out a raven to examine, you're putting yourself in a situation where the outcome is genuinely informative. If the hypothesis all ravens are black is false, if there are some non-black ravens out there, then there's a reasonable chance you might find one when you go looking for ravens. If you find a black raven instead, you've learned that this particular raven doesn't refute the hypothesis. That's a meaningful piece of information. You've gained evidence in a way that actually shifts your probabilities. This is sometimes called the ravens versus haystack problem. Looking for ravens among ravens is like looking for a needle in a small specific haystack. Looking for ravens among non-black things is like looking for a needle in a haystack the size of the entire universe. In the second case, you're almost certain not to find a raven, so the fact that you don't find one tells you almost nothing. The observation is consistent with the hypothesis, and so it confirms it in a minimal sense, but the confirmation is so weak as to be practically irrelevant. Here's another way to think about it, using concrete numbers to make the point clearer. Suppose there are 10,000 ravens in the world, and you're testing the hypothesis that all of them are black. Suppose also that there are 10 billion non-black things in the world. Now imagine you observe a black raven. You've checked 1 out of 10,000 ravens and found it to be black. That's a modest but meaningful fraction of the total population of ravens. You've reduced the space where a counterexample could be hiding. Now imagine you observe a green apple, confirming that this non-black thing is not a raven. You've checked 1 out of 10 billion non-black things. You've reduced the space of potential counterexamples by a truly negligible amount. Even if you observed 1,000,000 green apples, you'd still have barely scratched the surface of the non-black things in the world. The numbers make the asymmetry vivid. Yes, each non-black, non-raven confirms the hypothesis in principle, but the confirmation is diluted by the sheer size of the category you're sampling from. It's not that the apple provides no confirmation, it's that the confirmation is so slight, so minimal, that it might as well be zero. Meanwhile, observing ravens provides confirmation that is meaningfully stronger, because you're sampling from a much smaller and more directly relevant category. This resolution of the paradox has a certain elegance. It allows us to respect the logical equivalence between the two formulations of the hypothesis, while also honouring our intuition that raven observations are more informative than apple observations. We don't have to say that the logic is wrong, and we don't have to say that our intuitions are wrong. We just have to recognise that confirmation is a matter of degree, and that some observations, while technically confirming, are so weakly confirming that they don't play a meaningful role in our reasoning. But this resolution also invites further questions. If confirmation is a matter of degree, what determines the degree? How do we measure it? The Bayesian answer is that it depends on prior probabilities, the probabilities you assign to different hypotheses before you make any observations. But where do those prior probabilities come from? How do we set them in a rational way? These are deep questions in the philosophy of science and the foundations of statistics, and they don't have simple answers. The raven paradox, in drawing our attention to these issues, opens up a whole landscape of further inquiry. Another approach to resolving the paradox focuses on the idea of relevance. This approach says that we should distinguish between evidence that is logically consistent with a hypothesis and evidence that is genuinely relevant to testing that hypothesis. A green apple is consistent with all ravens are black, but it's not relevant because it doesn't tell us anything new or useful about ravens. Relevance, in this view, is not just about logical consistency. It's about informativeness, about whether the observation has the potential to change our state of knowledge in a meaningful way. This distinction between consistency and relevance is intuitively appealing. We can all recognize the difference between an observation that merely fails to contradict a hypothesis and an observation that actively supports it. When you observe a green apple, you're doing the former, but not the latter. The apple doesn't contradict all ravens are black, but it also doesn't give you any reason to increase your confidence in that claim. It's neutral or nearly so. By contrast, observing a black raven does give you a reason to increase your confidence, because it's an observation that bears directly on the subject matter of the hypothesis. But making this distinction precise turns out to be tricky. How do we define relevance in a way that's not circular or arbitrary? We can't just say that relevant evidence is evidence about ravens, because that would beg the question. We need a principled criterion for deciding which observations are relevant and which aren't. Some philosophers have tried to develop such criteria, often by appealing to the idea that relevant evidence is evidence that would have been different if the hypothesis were false. A black raven is relevant because if the hypothesis all ravens are black were false, you might have observed a non-black raven instead. A green apple is not relevant because even if the hypothesis were false, you'd still expect to observe a green non-raven when you pick up an apple. This gets us into the territory of counterfactual reasoning, thinking about what would have happened under different circumstances. Counterfactuals are slippery things, and using them to define relevance raises its own set of puzzles. But the basic idea has a certain appeal. It connects relevance to the notion of a genuine test, an observation that could have come out differently, and that would have meant something different if it had. Yet another approach to the paradox questions, the equivalence condition itself. Maybe, some philosophers have suggested, it's not actually true that logically equivalent hypotheses must be confirmed by the same evidence. Maybe confirmation is sensitive not just to the logical content of a hypothesis, but also to how that hypothesis is formulated or framed. All ravens are black, and all non-black things are non-ravens might be logically equivalent, but they suggest different ways of investigating the world, different domains of inquiry. When you say all ravens are black, you're making a claim about ravens, and that claim naturally directs your attention to ravens. When you say all non-black things are non-ravens, you're making a claim about non-black things, and that claim directs your attention elsewhere. Perhaps confirmation should track these differences in formulation, not just the underlying logical content. This approach is more radical, because it challenges one of the key assumptions that generates the paradox in the first place. If you reject the equivalence condition, the paradox loses its sting. You can say that observing a green apple confirms all non-black things are non-ravens, but does not confirm all ravens are black, even though the two hypotheses are logically equivalent. But this move has costs. It means giving up on a principle that seems deeply intuitive and rational. If two statements are logically equivalent, if they're just two ways of saying the same thing, shouldn't they be treated the same way epistemically? Abandoning the equivalence condition feels like a retreat from rationality, a concession that logic and evidence don't fit together as neatly as we'd like. There's also a more pragmatic way of thinking about the raven paradox, one that steps back from the formal philosophical debate and asks what the paradox teaches us about scientific practice. From this perspective, the paradox is a reminder that science doesn't proceed by mechanical application of confirmation rules. Scientists don't simply gather observations and tally up how much each one confirms or disconfirms their hypotheses. They make judgments about which observations are worth pursuing, which experiments are worth running, which evidence is worth collecting. These judgments depend on background knowledge, practical constraints, and an intuitive sense of what will be informative. A scientist investigating raven coloration would never think to study apples, not because apples logically fail to confirm the hypothesis, but because the scientist knows that studying apples would be a waste of time. The potential confirmation is too weak, the connection too remote, the effort too great for the minimal epistemic payoff. Better to go out and look at ravens, where each observation has a much higher chance of being informative. Science is about efficiency as well as logic. It's about directing your attention and resources to the questions and observations that will yield the most insight from this pragmatic standpoint. The raven paradox isn't really a paradox about confirmation at all. It's a lesson in why formal models of confirmation need to be supplemented with practical wisdom. The logic is fine, the math is fine, but human inquiry is not just logic and math. It's also judgment, intuition, and an understanding of context. The paradox shows us the limits of trying to reduce confirmation to a simple set of rules that can be applied mechanically without regard to background knowledge or the structure of the problem. Let's think about the paradox from yet another angle. Part of what makes it feel strange is that it seems to allow confirmation without any possibility of disconfirmation. When you observe a green apple, you're guaranteed to find that it's not a raven. There's no suspense, no risk, no chance of surprise. And this feels problematic, because good evidence is supposed to involve the possibility of being wrong. A meaningful test is one that could go either way, where the outcome is not predetermined. When you observe a raven, there's at least a theoretical possibility that it might not be black. When you observe an apple, there's no possibility, even in theory, that it might turn out to be a raven. This connects to a broader idea in the philosophy of science, the idea that good scientific hypotheses are those that are falsifiable, that make risky predictions which could turn out to be wrong. Karl Popper, one of the most influential philosophers of science, argued that what distinguishes science from non-science is precisely this willingness to put claims at risk of being refuted by evidence. A hypothesis that's compatible with any possible observation is not a scientific hypothesis. It's an empty claim that doesn't tell us anything about the world. By this standard, observing green apples seems like an impoverished way of testing all ravens are black, because the observation involves no real risk of falsification. But Popper's focus on falsification doesn't quite resolve the raven paradox, because the paradox is about confirmation, not falsification. No one disputes that the way to falsify all ravens are black is to find a non-black raven. The puzzle is about what confirms the hypothesis when you don't find a falsifying instance. Popper himself was skeptical of the whole idea of confirmation, arguing that hypotheses are never confirmed, only corroborated by surviving attempts at falsification. From his perspective, the paradox might be a symptom of taking confirmation too seriously in the first place. But most philosophers and scientists do think that evidence can support hypotheses, not just fail to refute them, so Popper's view doesn't fully dissolve the paradox for everyone. Another interesting dimension of the paradox emerges when you think about the role of randomness and sampling. The way evidence works in science often depends on how you gathered that evidence. If you randomly sample from a population and find certain patterns, that's more informative than if you selectively sample in a way that biases the results. Now, when you observe a black raven, you're typically doing so by going out and finding ravens, which is a kind of selective sampling. You're sampling from the population of ravens, not from the population of all things in the world. When you observe a green apple, you're sampling from the population of non-black things, or perhaps from the population of things in your kitchen. The informativeness of these observations depends on how the sampling was done. If you randomly selected an object from the universe and it happened to be a black raven, that would be much more informative than if you specifically sought out a raven. Similarly, if you randomly selected a non-black object and it happened to be a non-raven, that would provide some information, though not much, because the prior probability of picking a raven at random from the set of non-black things is already very low. The structure of the sampling process matters for how we interpret the evidence. Some philosophers have argued that the paradox arises because we're not being careful about the reference class, the population we're sampling from. When we say all ravens are black, we're making a claim about ravens, so the natural reference class is the set of all ravens. Evidence gathered by sampling from that class is directly relevant. When we say all non-black things are non-ravens, we're making a claim about non-black things, so the natural reference class is the set of all non-black things. Evidence gathered by sampling from that class is relevant to the reformulated hypothesis, but the two reference classes are so different in size and composition that evidence from one doesn't translate straightforwardly to evidence for the other, even though the hypotheses are logically equivalent. This line of thinking suggests that the equivalence condition needs to be qualified. Logically, equivalent hypotheses are confirmed by the same evidence only when that evidence is sampled from an appropriate reference class. A black raven confirms all ravens are black when you're sampling from ravens. A green apple confirms all non-black things are non-ravens when you're sampling from non-black things. But it doesn't follow that the apple confirms the raven hypothesis in any practical sense, because the reference classes are different. This resolution preserves the logic while blocking the counterintuitive conclusion. Let's also consider the psychological dimension of the paradox. Why does it feel so strange to say that a green apple confirms all ravens are black? Part of the answer may lie in how our minds naturally think about categories and evidence. Humans are not blank slates. We come equipped with cognitive biases and heuristics that shape how we reason. One of these biases is a tendency to focus on positive instances of the category we're interested in. If we're thinking about ravens, we naturally attend to ravens. If we're thinking about black things, we naturally attend to black things. It's cognitively unnatural to shift our attention to the complement of a category, to think about all the things that are not ravens or all the things that are not black. This psychological fact doesn't resolve the logical paradox, but it helps explain why the paradox feels paradoxical. Our intuitive sense of what counts as relevant evidence is shaped by these cognitive biases. When we're asked to consider non-black non-ravens as evidence about ravens, we're being asked to think in a way that goes against the grain of our natural cognitive tendencies. The paradox exploits this mismatch between our intuitive reasoning and the formal logic of confirmation. There's also a semantic aspect to consider. When we use the word confirms in everyday language, we typically mean something like provides good reason to believe or makes more credible. This is a normative or evaluative notion, not just a descriptive one. We're not just saying that the evidence is logically consistent with the hypothesis. We're saying that it gives us grounds to increase our confidence in the hypothesis. In this sense, confirmation is tied to rationality and justification. Observing a green apple may be logically consistent with all ravens are black, but it doesn't seem to provide a good reason to believe that claim. It doesn't make the claim more credible. So there's a gap between what we might call logical confirmation, mere consistency, and what we might call evidential confirmation, genuine epistemic support. Making this distinction helps clarify what's at stake in the paradox. The logical argument shows that green apples are logically consistent with the hypothesis and, in that sense, confirm it. Our intuition rebels because logical consistency isn't enough for evidential confirmation. We want evidence to do more than just fail to contradict the hypothesis. We want it to actively support the hypothesis in a way that gives us reason to believe it more strongly. And green apples don't do that, at least not in any meaningful degree. This brings us back to the Bayesian approach, which provides a framework for thinking about evidential confirmation in a more rigorous way. In Bayesian terms, evidence confirms a hypothesis if it increases the probability of the hypothesis being true. The amount of confirmation is measured by how much the probability increases. This framework allows us to say that green apples do confirm all ravens are black, but only infinitesimally, because they increase the probability of the hypothesis by an amount that's effectively zero. Meanwhile, black ravens confirm the hypothesis more substantially, because they increase the probability by a noticeable amount. The Bayesian approach also highlights the role of prior probabilities, the probabilities we assign before we make any observations. If your prior probability that all ravens are black is already very high, then observing additional black ravens won't change your belief much. If your prior probability is moderate, then the observations will have more impact. The informativeness of evidence depends on your starting point, on what you already believe or expect. This is both a strength and a weakness of the Bayesian framework. It's a strength because it captures the way evidence interacts with background knowledge. It's a weakness because it introduces a subjective element. Different people with different priors will be affected differently by the same evidence. The Raven paradox has been discussed and debated by philosophers for decades, and there's no single consensus resolution. Different philosophers favour different approaches, and some argue that the paradox reveals fundamental tensions that can't be fully resolved, only managed. But the ongoing discussion has been fruitful. leading to a richer and more nuanced understanding of how evidence works, how confirmation should be understood, and how logic relates to epistemology. One of the valuable lessons of the paradox is that formalization, while powerful, has its limits. When we try to capture intuitive concepts like evidence and confirmation in formal systems, we often find that the formal systems behave in ways that diverge from our intuitions. This doesn't necessarily mean that the formal systems are wrong or that our intuitions are unreliable. It means that the concepts are more subtle than they first appear, and that there's work to be done in bridging the gap between formalism and intuition. The paradox is a case study in this kind of conceptual work. It's also worth noting that the Raven paradox is part of a larger family of puzzles in the philosophy of science and epistemology. There are other paradoxes and problems that raise similar issues about confirmation, induction, and the nature of evidence. For example, there's the GRU paradox, introduced by Nelson Goodman, which challenges our assumptions about how observations support predictions. There's the problem of induction, famously articulated by David Hume, which questions whether we can ever be justified in inferring general laws from particular observations. These puzzles are interconnected, and insights from one can often shed light on others. The Raven paradox, despite its name and its focus on birds and apples, is not really about ravens or apples at all. It's about the structure of reasoning, the nature of evidence, and the relationship between logic and intuition. It's a thought experiment that uses simple, concrete examples to probe deep questions about how we know what we know and how we justify our beliefs. The examples are deliberately mundane: ravens, apples, colours, because the point is to show that even in the most ordinary contexts, when we think carefully about confirmation, we encounter puzzles that resist easy resolution. Let's think more concretely about what it would mean to take the paradox seriously in practice. Imagine you're an ornithologist who genuinely wants to test the hypothesis that all ravens are black. You have limited time and resources. What should you do? The logical argument suggests that you could stay in your office and examine non-black objects, tallying up each non-raven you find. But this would be absurd, and not just because it goes against scientific intuition. It would be absurd because it would be staggeringly inefficient. The number of non-black non-ravens is so vast that you could spend a lifetime examining them and still have barely made a dent in the total population. Meanwhile, each observation would provide only a microscopic amount of confirmation. By contrast, if you go out into the field and observe ravens directly, each observation is much more informative. Yes, you're examining a smaller number of objects, but those objects are drawn from the category you actually care about. You're testing the hypothesis in a direct, targeted way. The risk of finding a counterexample is real, even if small, and that's what makes the observations meaningful. This is why actual scientists investigating bird coloration would observe birds, not random objects. The paradox may show that non-black non-ravens logically confirm the hypothesis, but it also shows, perhaps inadvertently, why that logical fact doesn't translate into a practical research strategy. Here's another way to think about the pragmatic dimension. Science is not just about accumulating true beliefs. It's also about answering questions efficiently and reliably. A good scientific methodology is one that leads you to the truth with minimal wasted effort. Observing ravens is a good methodology for testing claims about ravens because it concentrates your efforts where they're most likely to pay off. Observing non-black non-ravens is a poor methodology, not because it's logically flawed, but because it's pragmatically inefficient. The Raven paradox in this light is less a paradox about confirmation and more a reminder that logic alone doesn't determine what counts as good science. There's also a meta-level lesson here about the nature of philosophical paradoxes in general. Paradoxes often arise when we take principles that seem obviously true and follow them rigorously to conclusions that seem obviously false. The principles and the conclusions are in tension, and we're forced to decide which to revise. Sometimes the lesson is that the principles need to be qualified or refined. Sometimes the lesson is that our intuitions about the conclusions are misleading. Sometimes the lesson is that the concepts involved are more complex than we realized and need to be unpacked or reconceptualized. In the case of the raven paradox, different philosophers have drawn different lessons. Some have refined the equivalence condition, arguing that it needs to be restricted or supplemented with additional criteria. Some have embraced the counterintuitive conclusion that green apples do confirm all ravens are black, but only trivially. Some have rejected the simple picture of confirmation that generates the paradox in the first place, arguing for a more complex, context-sensitive notion of evidential support. Each of these responses has something to teach us about the concepts of evidence and confirmation. Let's return once more to the green apple and think about what we learn from it. When you observe a green apple and note that it's not a raven, you're ruling out one possible state of the world, the state in which that particular green apple is a raven. But that state was never a live possibility. Your background knowledge already told you that apples are not ravens, that ravens are birds and apples are fruits, that they belong to entirely different categories of things. So the observation doesn't really change your state of knowledge. It doesn't tell you anything you didn't already know. This is the key difference between observing a green apple and observing a black raven. When you observe a raven and note that it's black, you're ruling out a possible state of the world that was genuinely uncertain before the observation, the state in which that particular raven is non-black. Your background knowledge tells you that ravens are typically black, but typically is not always. There's at least some chance, however small, that this raven might be an exception. So the observation does change your state of knowledge. It resolves an uncertainty that was real, even if slight. The Bayesian framework captures this difference in terms of how much the observation shifts your probabilities. Observing a black raven shifts your probability assignment in a meaningful way, because before the observation, there was some non-zero probability that the raven might not be black. Observing a green apple shifts your probability assignment in a negligible way, because before the observation, the probability that the apple might be a raven was already essentially zero. Both observations provide confirmation in the sense of being consistent with the hypothesis and ruling out possibilities, but the degree of confirmation is vastly different because the probabilities involved are vastly different. This probabilistic way of thinking also helps us understand why the size of the reference class matters so much. When you're sampling from a small class like the class of ravens, each observation tells you a significant fraction of what you need to know. When you're sampling from a massive class like the class of non-black things, each observation tells you almost nothing, because there are so many other things you haven't sampled. It's a matter of coverage. To adequately test a hypothesis by examining non-black things, you'd need to examine a significant fraction of all non-black things, which is impossible. To adequately test the hypothesis by examining ravens, you only need to examine a significant fraction of all ravens, which, while still challenging, is at least feasible in principle. The raven paradox also invites us to think about the difference between confirmation in theory and confirmation in practice. In theory, any observation that's consistent with a hypothesis and that rules out some possibility confirms the hypothesis to some degree. This is the formal, logical notion of confirmation. In practice, we only care about observations that shift our beliefs in a meaningful way, that tell us something we didn't already know, that reduce our uncertainty about the hypothesis. This is the pragmatic, epistemic notion of confirmation. The paradox arises because we sometimes conflate these two notions, treating them as if they were the same thing when they're actually different. Recognizing this distinction helps dissolve the paradox. We can say that green apples confirm all ravens are black in the formal sense without committing ourselves to the claim that they're useful or informative evidence in the practical sense. The logical argument shows that there's a sense in which apples confirm the hypothesis, but that sense is technical and abstract. Our intuitive resistance to the conclusion is based on the practical, epistemic sense of confirmation, where apples don't confirm the hypothesis in any meaningful way. Once we see that these are different senses of confirm, the tension eases, but even this resolution leaves some questions unanswered. What exactly is the relationship between formal confirmation and practical confirmation? When should we care about one versus the other? Are there contexts where the formal notion is what matters, or is the practical notion always what we should focus on? These questions don't have simple answers, and they connect to broader debates in epistemology and the philosophy of science about the role of formal methods in understanding human knowledge. It's also interesting to think about how the Raven paradox relates to confirmation in other domains, not just science. We make inferences and gather evidence in everyday life, in politics, in law, in personal relationships. We form beliefs about the world based on observations, and we update those beliefs as we learn new information. The structure of this reasoning is in many ways similar to the structure of scientific confirmation. We have hypotheses, we observe evidence, and we decide how much the evidence supports the hypotheses. So the lessons of the Raven paradox might apply more broadly than just to scientific methodology. For instance, imagine you're trying to decide whether all members of a certain group share a particular trait. You might observe members of the group and check whether they have the trait. This is like observing ravens and checking whether they're black. But you might also observe things that don't belong to the group and check whether they have the trait. This is like observing non-black things and checking whether they're ravens. The paradox suggests that both kinds of observations provide some confirmation, but that observations of group members are much more informative than observations of non-members. This insight might guide how you allocate your attention and how you weigh different kinds of evidence. Or consider a legal context. Suppose a prosecutor is trying to prove that all transactions by a particular company were fraudulent. They could examine the company's transactions and show that each one was fraudulent, or they could examine non-fraudulent transactions and show that none of them were conducted by the company. The second approach is logically equivalent to the first, but it would be much less persuasive to a jury, and for good reason. The first approach provides direct relevant evidence. The second approach provides evidence that's technically consistent with the claim, but not meaningfully informative. The Raven paradox helps explain why these two approaches feel so different, even though they're logically equivalent. The paradox also touches on themes in the philosophy of language and the theory of meaning. The fact that all ravens are black and all non-black things are non-ravens are logically equivalent, but feel so different suggests that meaning is not purely a matter of logical content. The way a sentence is formulated, the concepts it foregrounds, the cognitive associations it triggers, all of these matter for how we interpret and use the sentence. Two sentences can have the same truth conditions, the same logical form, and yet mean different things in some richer, more pragmatic sense. This connects to a broader philosophical question about whether meaning is compositional, whether the meaning of a sentence is determined entirely by the meanings of its parts and how they're put together, or whether meaning also depends on context, use, and other factors that go beyond the sentence itself. The Raven paradox suggests that at least when it comes to confirmation and evidence, context and formulation matter in ways that pure logic doesn't capture. Let's also consider the temporal dimension of confirmation. Scientific understanding develops over time. Hypotheses are proposed, tested, refined, replaced. Evidence accumulates gradually, and our confidence in various claims rises and falls as new observations come in. The Raven paradox is often presented as a static puzzle. Here's a hypothesis, here's an observation. Does the observation confirm the hypothesis? But in reality, confirmation is a dynamic process that unfolds over time. In this dynamic context, the question of what counts as good evidence becomes even more complex. Early in the investigation of a phenomenon, when we know very little, almost any observation might be informative. As our knowledge grows, the bar for what counts as informative rises. We become more selective about which observations are worth pursuing because we have a better sense of what we already know and what questions remain open. The Raven paradox, with its static setup, doesn't capture this dynamic aspect of scientific inquiry, but thinking about the paradox in a dynamic context can shed additional light on why some evidence is more valuable than others. For example, suppose you're just beginning to study ravens and you have no idea what colour they are. In that state of ignorance, observing a green apple and confirming that it's not a raven might actually be somewhat informative, because you don't yet know much about what things are ravens and what things aren't. But suppose you've already observed thousands of objects and have developed a good sense of what ravens look like and where they're found. In that state of knowledge, observing another green apple tells you nothing you didn't already know. The informativeness of the same observation depends on your background knowledge, which changes over time as you learn more. This suggests yet another way of thinking about the paradox. It's a reminder that evidence doesn't exist in a vacuum. What counts as good evidence depends on what you already know, what questions you're trying to answer, and what stage of inquiry you're in. The paradox arises because it strips away all this context and asks a decontextualized question about confirmation. When we restore the context, the paradox becomes less puzzling, because we can see why different observations have different value in different circumstances. There's also a pedagogical value to the Raven paradox. It's a wonderful teaching tool for introducing students to the philosophy of science and the philosophy of language. It's simple enough to grasp quickly. You don't need any advanced mathematics or technical knowledge to understand the basic setup, but it's deep enough to raise genuinely difficult questions that don't have easy answers. It's the kind of problem that makes you think, that challenges your assumptions, that reveals hidden complexities in concepts you thought you understood. For students learning about the scientific method, the paradox is a useful reminder that science is not just about following recipes or applying formulas. It's about making judgment calls, about deciding which observations are worth pursuing, about recognizing the difference between technically correct and practically useful. These are skills that can't be captured in a simple algorithm. They require experience, insight, and a feel for the subject matter. The paradox highlights the gap between formal methodology and actual practice. For students learning about logic and language, the paradox is a good illustration of how logical equivalence doesn't always translate into equivalence of meaning or use. Two sentences can be logically equivalent without being interchangeable in all contexts. This is an important lesson for understanding the relationship between logic and natural language, and for recognizing the limits of a formal analysis. The Raven paradox has also inspired work in other areas of philosophy and even in other disciplines. In statistics, for example, there's been discussion about how the paradox relates to different approaches to hypothesis testing and statistical inference. In cognitive science, the paradox has been used to explore how people actually reason about evidence and whether their reasoning conforms to normative standards of rationality. In artificial intelligence, the paradox raises questions about how to program machines to make reasonable inferences from observations. These connections show that the paradox is not just an isolated puzzle, but part of a larger web of questions about reasoning, evidence, and knowledge. Understanding the paradox can help us understand these other questions, and vice versa. It's a node in a network of philosophical and scientific ideas, and exploring it can lead you in many different directions. As we come to the end of this long exploration, it's worth stepping back and thinking about what the Raven paradox ultimately teaches us. At one level, it's a lesson in humility. It shows that even simple common sense concepts like evidence and confirmation are more complicated than they seem. When we try to make these concepts precise, we run into difficulties. This doesn't mean we should give up on precision or formalization, but it does mean we should approach these tools with a certain caution and flexibility. Formal methods are powerful, but they're not magic. They don't automatically solve all our problems, and they can sometimes create new puzzles that require further thought. At another level, the paradox is a lesson in the importance of context and judgment. Logic can tell us what's consistent with what, and mathematics can tell us how to update probabilities, but deciding what observations to pursue, what evidence to value, what hypotheses to take seriously, these are not purely logical or mathematical questions. They involve judgment, background knowledge, and an understanding of the specific problem you're trying to solve. The Raven paradox reminds us that good science is not just a matter of applying rules, it's a matter of wisdom and insight. At yet another level, the paradox is a lesson in the value of philosophical inquiry. Philosophy often deals with questions that don't have clear, definitive answers, questions where different perspectives have different strengths and weaknesses. This can be frustrating if you're looking for certainty, but it can also be liberating and enriching. By grappling with the Raven paradox, we're not just learning about ravens or confirmation. We're learning how to think more carefully, how to recognize hidden assumptions, how to balance different intuitions and principles. These are valuable skills that extend far beyond philosophy. The paradox also invites a certain kind of playfulness, a willingness to entertain strange ideas and see where they lead. If green apples really do confirm facts about ravens, what would that mean? How would we make sense of it? By following the logic wherever it goes, even when it leads to counterintuitive conclusions, we open up new ways of thinking about familiar concepts. We discover that the world of ideas is richer and more surprising than we might have guessed. And finally, the paradox is a reminder of the beauty and mystery of reasoning itself. The fact that we can think about thinking, that we can reflect on how we gather evidence and justify our beliefs, that we can notice paradoxes and puzzles and work to resolve them. This is one of the remarkable capacities of the human mind. The Raven paradox is a small monument to this capacity, a testament to our ability to question, to analyze, to wonder. So when you observe a green apple, you're not learning much about ravens, at least not in any practical sense. But you might be learning something about evidence, about logic, about the subtle relationship between form and content, between theory and practice. You might be learning that confirmation is not a simple, univocal notion, but a complex, multifaceted one that depends on context, background knowledge, and the specific question you're asking. You might be learning that philosophy has something valuable to teach us about the structure of reasoning and the nature of justification. The green apple sits there on the table, ordinary and unremarkable. It's green. It's an apple. It's not a raven. These simple facts are consistent with the hypothesis that all ravens are black. In a technical, logical sense, they confirm that hypothesis, but they don't tell you much. They don't shift your beliefs in any meaningful way. They don't answer the question you're really asking when you ask about ravens. And yet, by thinking carefully about why they don't, by exploring the paradox they generate, you can learn a great deal about how evidence works, how confirmation should be understood, and how to think more clearly about the relationship between logic and knowledge. This is the gentle landing the paradox offers. It doesn't overturn science or declare logic invalid. It doesn't make knowledge impossible or confirmation arbitrary. It simply asks us to be more thoughtful, more careful, more aware of the complexities involved in reasoning from observations to conclusions. It asks us to recognize that formal principles are valuable but not sufficient, that intuition is important but not infallible, and that understanding how we know what we know requires both rigorous analysis and pragmatic wisdom. The raven paradox, in the end, is not a barrier to understanding, but a pathway to deeper insight. By wrestling with it, by exploring its implications, by considering different ways of resolving it, we come to understand the concept of evidence more fully. We learn that evidence is not just data points that either confirm or disconfirm hypotheses in a simple, mechanical way. Evidence is information that shifts our state of knowledge, that reduces our uncertainty, that helps us answer questions we care about. And what counts as good evidence depends on the context, on what we're trying to learn, on what we already know, and on the structure of the problem we're investigating. When you see a black raven, you're seeing something that matters for understanding ravens. When you see a green apple, you're seeing something that matters for understanding apples, or perhaps for understanding fruits or green things or objects in your kitchen. The apple happens to be logically consistent with a hypothesis about ravens, and in that minimal sense, it provides a whisper of confirmation, a trace of evidence so faint it's hardly worth mentioning. But it doesn't matter for understanding ravens in any practical, meaningful way. And that's okay. Not every observation has to matter for every hypothesis. Not every piece of evidence has to be equally informative. The world is full of observations, and we have to be selective about which ones we attend to, which ones we value, which ones we use to guide our beliefs and our actions. The paradox teaches us to be thoughtful about these choices, to recognize that confirmation is a nuanced concept, to understand that logic and intuition both have roles to play in making sense of evidence. It teaches us that philosophy, at its best, doesn't give us easy answers, but helps us ask better questions and think more clearly about the concepts we use every day. And it teaches us that even the simplest observations, a black raven, a green apple, can become windows into deep questions about knowledge, reasoning, and the nature of understanding itself. The next story is about to begin. Please relax and enjoy. Probability shapes the way we move through the world, quietly guiding countless everyday decisions. When you check the weather forecast and see a 95% chance of sunshine, you probably leave your umbrella at home. When you buckle your seatbelt, you're not expecting an accident. The probability of one on any given trip is vanishingly small. We live comfortably with these probabilities, treating events that are extremely unlikely as if they simply won't happen. This mental shortcut serves us well most of the time. It would be exhausting to maintain constant awareness of every remote possibility, so we round things off. We take what is highly probable, and for practical purposes, treat it as certain. This habit feels not just convenient but reasonable. After all, if something has a 99.999% chance of happening, isn't it essentially guaranteed? And if something has that same percentage chance of not happening, isn't it essentially ruled out? In daily life, the difference between almost certain and certain rarely matters. You plan your day around high probabilities, and most of the time, things work out roughly as expected. The weather is usually close to what was forecast. The bridge you drive over doesn't collapse. The restaurant you visit doesn't give you food poisoning. These aren't certainties, but they're close enough that you'd feel silly worrying about them. Yet there's a curious puzzle lurking in this everyday reasoning, one that emerges when you push this habit just a bit further. It's called the lottery paradox, and it reveals something subtle and fascinating about how probability and belief interact. The paradox doesn't involve any exotic physics or abstract mathematics. It starts with something utterly mundane. A lottery. Not a real lottery necessarily, but the kind of simple, fair lottery you might imagine for the sake of a thought experiment. And from this simple starting point, it leads to a genuinely perplexing conclusion about what it means to believe something rationally. The charm of the lottery paradox is that it sneaks up on you. It doesn't announce itself with flashing lights or dramatic contradictions. Instead, it emerges gradually, step by step, each step seeming perfectly sensible on its own. You begin with a situation everyone can understand. You make a series of judgments that each feel entirely reasonable, And then suddenly you realize those judgments have led you somewhere impossible. The paradox doesn't tell you that you've made a mistake. It just quietly points out that something has gone wrong, and it invites you to figure out what. So let's begin where the paradox begins, with a perfectly ordinary lottery. Imagine a lottery with a very large number of tickets. To make things concrete, let's say there are 1 million tickets. Each ticket has a unique number, from 1 to 1 million. The lottery is completely fair. That means every ticket has exactly the same chance of winning. There are no tricks, no biases, no hidden patterns. The winning ticket will be selected by some genuinely random process. Maybe a computer generates a random number, or maybe numbered balls are drawn from a tumbler. The details don't matter. What matters is that the process is fair, and everyone agrees it's fair. In this lottery, exactly one ticket will win. That's guaranteed. It's part of the setup. When the lottery is over, one ticket will be the winner, and all the other tickets will be losers. This isn't a probability, it's a certainty. The lottery's rules ensure that there must be a winner. So we know with complete confidence that when the dust settles, 999,999 tickets will have lost, and one ticket will have won. Now consider any particular ticket in this lottery. Let's start with ticket number 1. What's the probability that ticket number 1 will win? Since the lottery is fair and there are 1 million tickets total, the probability is 1 in 1 million. That's a very small probability. It's 0.0001%. If you held ticket number 1, you would not expect to win. You might hope to win, certainly, but you wouldn't expect it. The odds are overwhelmingly against you. Turn this around and consider the probability that ticket number 1 will lose. That probability is 999,999 out of 1 million. In other words, 99.9999%. This is an extremely high probability. If you were betting on whether ticket number 1 would lose, you'd be making a very safe bet. The chance of being wrong is 1 in a million. Here's where things start to get interesting. Suppose someone asks you, do you believe ticket number 1 will lose? How should you answer? Well, given the probabilities, it seems entirely reasonable to say yes. You believe ticket number 1 will lose. After all, it almost certainly will lose. The probability is so close to 100% that the difference barely seems worth mentioning. For any practical purpose, you can treat it as a foregone conclusion. Ticket number 1 will lose. This isn't a wild guess or a superstitious hunch. It's a rational judgment based on solid probabilistic reasoning. If you were making decisions based on this belief, if you were, say, deciding whether to plan a celebration party for the holder of ticket number 1, you would be entirely justified in not bothering. The ticket will lose. You believe it will lose. That belief seems not just permissible, but appropriate. Now consider ticket number 2. The exact same reasoning applies. Ticket number 2 has a 1 in 1 million chance of winning, which means it has a 99.9999% chance of losing. So it seems just as reasonable to believe that ticket number 2 will lose. And ticket number 3, same story. Ticket number 4, also the same. In fact, for any ticket you pick, the reasoning is identical. Each ticket has a minuscule chance of winning and an overwhelming chance of losing. For each individual ticket, believing it will lose seems like the rational thing to do. You can imagine going through the tickets one by one. Ticket number 1 will lose. Ticket number 2 will lose. Ticket number 3 will lose. You continue through the hundreds, the thousands, the hundreds of thousands. Each time the judgment feels solid. Each ticket, considered on its own, almost certainly will not win. So for each ticket, it's rational to believe it will lose. The reasoning is repetitive, but it's also consistent. There's no point at which you switch methods or apply different standards. Every ticket gets the same treatment, and every ticket gets the same verdict. But now a problem appears. If you believe ticket number 1 will lose, and you believe ticket number 2 will lose, and you believe ticket number 3 will lose, and you continue this all the way through ticket number 1 million, then you believe something very specific about each ticket. And when you put all these beliefs together, they seem to add up to a collective belief. You believe that all the tickets will lose. This is where the paradox bites. You can't rationally believe that all the tickets will lose, because that's not just improbable, it's impossible. The lottery guarantees that one ticket will win, so the collective belief that all tickets will lose contradicts a known fact. It's not merely false, it's necessarily false. Yet this impossible belief appears to follow directly from a series of individually reasonable beliefs. Each step felt justified, each individual judgment seemed rational, but the endpoint is absurd. This is the lottery paradox in its purest form. You start with beliefs that each seem perfectly rational. You combine them in a straightforward way, and you end up with a conclusion that cannot possibly be true. Something has gone wrong, but it's not immediately obvious what. Each individual belief seems fine. The method of reasoning seems fine, yet the result is clearly broken. At first glance, you might think the problem is obvious and easily fixed. Maybe you just shouldn't believe that every ticket will lose. Maybe the solution is to remain agnostic about the collective outcome. But that doesn't quite resolve the tension, because the question isn't really about the collective outcome. It's about the individual tickets. The paradox asks, is it rational to believe, of ticket number 1 specifically, that it will lose? And if the answer is yes, then why isn't it also rational to believe the same thing about ticket number 2? And ticket number 3? The paradox forces you to either accept the absurd conclusion or reject one of the seemingly reasonable steps that led to it. To understand why this is genuinely puzzling, it helps to think about what we usually expect from rational belief. In everyday reasoning, we tend to assume that rational beliefs should fit together in a logically coherent way. If you rationally believe that it's raining, and you rationally believe that you forgot your umbrella, then it seems you should also rationally believe the combination. It's raining, and you forgot your umbrella. This principle is sometimes called closure under conjunction. It says that if you believe A and you believe B, then you should believe A and B together. This principle seems almost too obvious to state. It's hard to imagine a conception of rational belief that doesn't respect it. After all, if you genuinely believe two things, why wouldn't you believe them together? Denying closure would seem to allow a strange kind of compartmentalized thinking, where you could hold beliefs that you simultaneously acknowledge don't fit together. That seems irrational, or at least very odd. The lottery paradox puts pressure on this principle. It suggests that you can have many individual beliefs, each one highly rational, that you nonetheless should not combine into a single joint belief. You can rationally believe that ticket 1 will lose, and rationally believe that ticket 2 will lose, and so on, without rationally believing that all tickets will lose. This means that rational belief, in the context of probabilistic reasoning, might not be closed under conjunction. You can believe each part without believing the whole. This is a surprising and somewhat uncomfortable conclusion. It challenges a deeply intuitive idea about how beliefs should work. But before accepting it, it's worth exploring why the individual beliefs seemed rational in the first place. What exactly are we doing when we say we believe that ticket number 1 will lose? One way to think about it is that we're making a judgment based on very high probability. We're not claiming absolute certainty. We're not saying it's metaphysically impossible for ticket 1 to win. We're just saying it's so unlikely that we're willing to treat it as a settled matter. In ordinary language, we'd say we believe it will lose. But what does that word believe really mean in this context? This is where the paradox starts to reveal something important. In everyday speech, believe is a bit of a blunt instrument. We use it to cover a wide range of confidence levels. Sometimes we believe things with rock-solid certainty, mathematical truths, for instance, or the fact that we exist. Other times, we believe things with high confidence, but not absolute certainty. The sun will rise tomorrow. The grocery store will be open at its usual time. And sometimes we believe things with less confidence still. That it probably won't rain today. That the traffic won't be too bad. In all these cases, we use the same word, believe. The lottery paradox exploits this blurriness. It takes a case where believe is being used in the high confidence but not certainty sense and asks what happens when you scale it up. If you're 99.9999% confident that ticket 1 will lose, is that enough to count as belief? Most people would say yes. That's about as confident as you can be about anything in the real world. But then, if you're equally confident about every single ticket, the paradox asks, does that mean you believe the conjunction of all those statements? And if you do, you've just committed yourself to believing something impossible. The problem is that high probability and certainty are not the same thing, even when the probability is very, very high. Certainty has a special property. If you're certain of A and certain of B, then you're certain of A and B together. Certainty is perfectly preserved under conjunction. But probability doesn't work that way. If you're 99% confident of A and 99% confident of B, you're not necessarily 99% confident of A and B together. In fact, as you combine more and more independent high probability statements, the probability that they're all true drops. Consider the lottery tickets again. The probability that ticket 1 loses is 0.999999. The probability that ticket 2 loses is also 0.999999. But the probability that both ticket 1 and ticket 2 lose is not 0.999999, it's 0.99999 multiplied by 0.99999, which is slightly less. When you extend this to all 1 million tickets, the probability that all of them lose is not 0.99999. It's 0.999999 raised to the power of 1 million. And that number is essentially zero. In fact, it's not just close to zero, it is zero because we know one ticket must win. This calculation reveals the heart of the paradox. Each individual belief has an extremely high probability of being true. But the probability that all the beliefs are true together is not high, it's zero. So if you're treating I believe X as meaning X has a very high probability, then each individual belief statement seems justified. But if you're also assuming that believing each of A, B, C, and so on means you should believe A and B and C, and so on, then you're in trouble. Those two principles collide in the lottery case. So what should you do? One option is to reject the idea that rational belief is closed under conjunction. You could say that it's perfectly fine to believe each individual statement without believing their conjunction, as long as the individual statements are based on high probability. This might feel strange at first, but it has some intuitive support. After all, you know going into the lottery that exactly one ticket will win. You're not surprised when a ticket wins. You just don't know which one. So maybe it's reasonable to maintain a kind of distributed confidence, high confidence about each individual ticket losing, combined with an acknowledgement that the collective belief would be false. This approach has a certain elegance. It respects the probabilistic reasoning that made each individual belief seem rational, and it avoids the absurd conclusion by denying that those beliefs need to combine in the usual logical way. Rational belief on this view is more flexible than pure logic. It can tolerate a kind of structured inconsistency, where you hold many beliefs that you know can't all be true together, as long as each one is individually well supported. But this approach also has costs. It means giving up on a very natural principle about how beliefs should cohere. It means accepting that a rational person might in some sense believe contradictory things, not in the sense of believing both P and not P, but in the sense of believing a set of things that logically entail something they know to be false. That's a departure from traditional ideas about rationality, and some people find it unsettling. Another option is to raise the bar for what counts as belief. Maybe you shouldn't call it a belief unless the probability is even higher than 99.9999%. Maybe you need something closer to absolute certainty, before you're entitled to use the word believe. On this view, the mistake in the lottery case is saying you believe each ticket will lose. You don't believe it. You just think it's very likely. Belief requires a higher standard, one that's safe under conjunction. This approach preserves the closure principle, but at a cost. It makes belief very demanding. In a million-ticket lottery, you can't believe any individual ticket will lose, because the probability, while very high, isn't high enough. In fact, on this view, you might not be able to believe much of anything about the real world, because very few things are certain enough to meet the standard. This seems overly restrictive. It doesn't match how people actually use the word believe, and it would make everyday reasoning extremely cumbersome. A third option is to say that what counts as rational belief depends on context. Maybe in some contexts, a 99.9999% probability is enough to justify belief, and in other contexts it isn't. The context might include things like what's at stake, how many beliefs you're aggregating, and what you're going to do with those beliefs. In a low-stakes context where you're reasoning about a single ticket, maybe it's fine to believe it will lose. In a higher stakes context where you're reasoning about all the tickets together, maybe you need to be more careful. This contextualist approach has some appeal. It captures the intuition that rationality isn't one size fits all, and it allows for flexibility in how we apply the concept of belief. But it also introduces complexity. It means there's no simple answer to the question, do you believe ticket 1 will lose? The answer depends on what you're doing with that belief and how it fits into your broader reasoning. This might be realistic, but it also makes the paradox harder to resolve cleanly. A fourth option, related to the third, is to distinguish between different kinds of mental states. Maybe there's a difference between believing something and merely accepting it for practical purposes. When you say, ticket 1 will lose, maybe you're not expressing a full-fledged belief. You're just accepting the statement as a working assumption, something you're willing to act on in most contexts. Acceptance is more provisional, more context-sensitive, and more pragmatic than belief. And importantly, acceptance doesn't need to be closed under conjunction. You can accept each of many statements individually without accepting their conjunction. This distinction has some philosophical precedent. It allows you to make sense of how scientists often work, for instance. A scientist might accept a theory for research purposes without fully believing it's true. They use it as a framework, a tool, something to work with, but they remain open to revising it, and they don't commit to it in the same deep way they might commit to, say, the belief that they exist. In the lottery case, you might accept that ticket 1 will lose, accept that ticket 2 will lose, and so on, without accepting that all tickets will lose. This avoids the paradox while preserving something close to the original intuition. Each of these responses has strengths and weaknesses, and philosophers continue to debate which, if any, is the right way to think about the lottery paradox. What's remarkable is that such a simple setup can generate such deep and persistent disagreement. The lottery isn't a complicated scenario. The probabilities aren't hard to calculate. Yet the question of how to think about belief in this context remains genuinely open. Part of what makes the paradox so durable is that it touches on something fundamental about how human minds handle uncertainty. We don't experience probabilities directly. We experience something more like degrees of confidence. When you think about ticket 1, you feel very confident it will lose. That feeling of confidence is what prompts you to say you believe it will lose. But feelings of confidence don't automatically track the subtleties of probabilistic reasoning. Your mind doesn't naturally compute the joint probability of a million independent events. It just takes each event one at a time and registers high confidence about each one. This is efficient in a way. It would be cognitively overwhelming to constantly track the interactions between all your probabilistic beliefs. So your mind uses shortcuts. It treats high confidence as if it were certainty, because in most everyday contexts that's close enough. You don't need to worry about the 1 in a million chance that your chair will collapse when you sit down, or that the water you drink is actually poison, or that the sun won't rise tomorrow. These things are possible in principle, but their probabilities are so low that you can safely ignore them. The lottery paradox reveals the limit of this shortcut. It constructs a scenario where you're forced to apply the shortcut many times in a row, and where the cumulative effect makes the shortcut break down. Each individual application seems fine. Each ticket, considered alone, really is overwhelmingly likely to lose. But when you aggregate a million such judgments, the approximation fails. The thing you are treating as certain turns out not to be certain after all, and the difference matters. In a sense, the paradox is a reminder that probability and certainty are different in kind, not just in degree. A 99% probability is not just a little bit less than certainty. It's a fundamentally different thing. And a 99.9999% probability, while much closer to certainty, is still not the same. As long as there's any gap at all, that gap can be exploited by scaling things up. The lottery paradox is the result of that exploitation. This has implications beyond lotteries. Think about large, complex systems made up of many components. Suppose you're managing a system with 1 million parts, and each part has a 99.9999% or no reliability rate. For any individual part, it's very reasonable to believe it will function correctly. But should you believe all million parts will function correctly at the same time? The math says no. Even though each part is highly reliable, the chance that all of them work perfectly is vanishingly small. In fact, with 1 million parts each having a 1 in a million failure rate, you'd expect about 1 failure on average. You don't know which part will fail, just as you don't know which lottery ticket will win, but you can be confident something will go wrong somewhere. This is why engineers build redundancy into complex systems. They don't treat high reliability as if it was certainty. They account for the fact that when you have enough components, even unlikely failures become likely at the system level. The lottery paradox captures the same insight in a purer form. It's not about practical engineering, it's about the logical structure of belief and probability, but the lesson translates. You can also see the paradox at work in other kinds of large-scale reasoning. Consider a weather forecaster who makes predictions for 1,000 different days. For each individual day, they might be 99% confident in their prediction. But should they be 99% confident that all 1,000 predictions will be correct? Clearly not. Even with high accuracy, 10 wrong predictions would be expected. The forecaster knows this. They don't believe all their predictions will be right, but for each individual prediction, they might well believe it will be right, because the probability is high enough. The structure is the same as the lottery, or consider a medical test that's 99.9% accurate. If you test negative, it's very reasonable to believe you don't have the disease. But if 1 million people are tested, and each person believes their own result, then collectively, they're believing things that can't all be true. About 1,000 people will get false results. The reasoning about individual cases seems solid, but the aggregate reasoning breaks down. These examples show that the lottery paradox isn't just an abstract puzzle. It reflects a real tension in how we think about uncertainty in the world. We make confident judgments about individual cases based on high probabilities. We often have to, because perfect certainty is rarely available. But when we're dealing with many cases, those confident judgments can lead us astray if we're not careful. The paradox is a warning about the limits of treating high probability as if it was certainty. What's comforting in a way is that the paradox doesn't imply that rationality itself is broken. It doesn't show that rational thinking is impossible, or that we should give up on making probabilistic judgments. Instead, it shows that we need to be thoughtful about how we use language like believe in probabilistic contexts. It shows that rational thinking involves more than just logic. It also involves calibration, being aware of how confidence scales, how probabilities combine, and when the shortcuts we usually rely on might fail. The paradox also highlights the limits of ordinary language. Words like believe, know, and certain evolved for everyday communication, not for precise reasoning about probability. They're fuzzy at the edges. They don't map cleanly onto mathematical concepts like probability and certainty. The lottery paradox lives in that fuzziness. It's a case where our ordinary way of talking about belief leads to something that sounds contradictory, even though the underlying probabilities are perfectly clear and consistent. In that sense, the paradox is less about belief itself and more about how we talk about belief. It's a semantic puzzle as much as a logical one. The probabilities are straightforward. The logic is straightforward. The confusion arises when we try to describe the situation using everyday language, and we find that the language doesn't quite fit. We say we believe ticket 1 will lose, and that seems right. We say we believe ticket 2 will lose, and that also seems right. But we can't say we believe all tickets will lose, and that creates a mismatch. The language of belief doesn't scale in the way we'd expect. One way to resolve this is to be more precise in how we talk. Instead of saying, I believe ticket 1 will lose, you could say, I assign a 99.9999% probability to ticket 1 losing. That's more cumbersome, but it's also more accurate. And importantly, it doesn't trigger the same paradox. You can assign a 99.9999% probability to ticket 1 losing, and another 99.9999% probability to ticket 2 losing, and so on, without any contradiction. The probabilities don't need to be closed under conjunction in the same way beliefs seem to be. You can have a 99.9999% confidence in each individual event, while having a 0% confidence in all of them happening together, and that's perfectly coherent. But this solution, while technically correct, doesn't quite capture how people actually think. Most people don't walk around assigning numerical probabilities to everything. They have beliefs, hunches, expectations, and degrees of confidence, but these are usually qualitative rather than quantitative. The language of belief is natural and intuitive, even if it's not always precise. The challenge is to understand how that natural language relates to the more precise language of probability, and where the translation breaks down. The lottery paradox is a useful tool for exploring that relationship. It's a clean, simple case where the breakdown is obvious. It forces you to confront the gap between I believe this and this has a very high probability. It makes you think about whether those two things are the same, and if not, how they differ. And it invites you to consider how rational belief should be understood in a world where certainty is rare and probability is everywhere. There's something almost meditative about thinking through the paradox slowly. You start with a situation that feels completely ordinary. A lottery with tickets, with one winner, nothing exotic, nothing hard to imagine. And then you follow the reasoning, step by step, carefully. Each step is small, each step makes sense. And then at the end, you arrive somewhere strange. The strangeness isn't loud or dramatic. It's quiet, subtle, almost gentle. It's just the realization that something you thought was simple is actually a bit more complicated than you expected. This kind of realization is part of what makes philosophy engaging. It's not about finding definitive answers. It's about noticing things, questioning assumptions, and appreciating the complexity that hides beneath the surface of everyday reasoning. The lottery paradox does this beautifully. It takes a mundane scenario and uses it to reveal something deep about belief, probability, and rationality. It doesn't tell you what to think. It just shows you that the question is harder than it first appeared. And that's okay. In fact, it's better than okay. It's part of how understanding deepens. You start with a simple picture of how things work. You notice a problem with that picture. You explore different ways to fix the problem, each with its own trade-offs. You don't necessarily arrive at a final answer, but you end up with a richer, more nuanced understanding of the terrain. The paradox is a guide on that journey. As you lie here, Thinking about tickets and probabilities, there's a certain calm that comes from recognizing the limits of certainty. The world is full of uncertainty. Most things are probable rather than certain. We navigate that uncertainty with mental shortcuts, rough and ready heuristics, and a willingness to round off the rough edges. Most of the time, that works fine. But every now and then, a paradox like this one reminds us that the shortcuts aren't perfect. They have limits. And understanding those limits is part of being a careful thinker. The lottery paradox doesn't demand that you fix everything right now. It doesn't insist that you choose one solution over another. It just asks you to notice the problem, to sit with it, to think about it. And in that sitting and thinking, there's a kind of quiet satisfaction. Not the satisfaction of solving a puzzle completely, but the satisfaction of seeing the puzzle clearly, of understanding its shape and structure, of appreciating why it's interesting. There's also something reassuring about the fact that the paradox has been around for a long time and smart people still disagree about how to resolve it. It means you're not expected to have all the answers. It means the questions are genuinely difficult, and thinking about them carefully is a worthwhile activity in itself. You're not failing if you don't arrive at a definitive conclusion. You're engaging with a deep issue, turning it over in your mind, exploring its facets. The paradox invites patience. It's not the kind of problem you solve quickly. It's the kind of problem you think about over time, returning to it occasionally, seeing it from different angles. Each time you return, you might notice something new, a new implication, a new connection, a new way of thinking about it. The paradox becomes familiar, but it doesn't become boring. It remains interesting because it touches on fundamental questions that don't have easy answers. In the quiet of the moment, with your mind turning over these ideas gently, you can appreciate the paradox for what it is. A beautiful example of how simple assumptions can lead to complex conclusions. It's a reminder that rationality is subtle, that language is imperfect, and that probability is both powerful and tricky. It's a small window into the larger project of understanding how minds work, how beliefs form, and how we make sense of a world that rarely offers certainty. And as your thoughts begin to drift, as the details of tickets and probabilities start to blur into the background, what remains is a sense of intellectual tranquility. The paradox isn't something to be anxious about. It's something to contemplate, to explore, to appreciate. It's a gentle puzzle, a quiet mystery, a small corner of the vast landscape of human thought. And there's something deeply restful about that, about engaging with ideas not because you have to solve them immediately, but because they're worth thinking about, because they reveal something about the world and about the mind's encounter with the world. The lottery paradox, in the end, is a paradox about humility. It's about recognizing that even our most confident beliefs might not fit together in the ways we expect. It's about accepting that almost certain and certain are genuinely different, even when the difference seems vanishingly small. It's about understanding that rational thinking isn't just about following rules. Mechanically, it's about being sensitive to context, to scale, to the ways in which many small probabilities can add up to something surprising. This humility doesn't mean giving up on confidence or retreating into skepticism. It just means being aware of the structure of your beliefs, of how they relate to probabilities, of when it's safe to combine them and when it's not. It means appreciating that rationality is a skill, not a formula, and that part of that skill is knowing when your usual shortcuts might lead you astray. In the context of the lottery, this means being comfortable with a certain kind of cognitive tension. You can believe, in a practical sense, that ticket one will lose. You can act on that belief, plan around it, use it to guide your decisions. But at the same time, you can hold lightly to the idea that this belief, when multiplied across all tickets, doesn't create a larger belief that all tickets will lose. You can maintain both the individual confidence and the collective uncertainty. It's a subtle balancing act, but it's one that reflects the reality of probabilistic reasoning. This balancing act is something we do all the time, often without noticing. When you drive to work, you believe you'll arrive safely, even though you know that car accidents happen. When you cook dinner, you believe the food won't make you sick, even though you know that food poisoning is possible. When you check your email, you believe it won't contain a catastrophic virus, even though you know that such things exist. In each case, you're holding a high probability belief, while implicitly acknowledging that the probability isn't 100%. The lottery paradox just makes this dynamic explicit and shows what happens when you scale it up. By making it explicit, the paradox gives you a chance to think about it more carefully, to understand the mechanisms at work, to see how probability shapes belief. And that understanding, even if it doesn't lead to a neat resolution, is valuable. It makes you a more thoughtful reasoner. It helps you avoid certain kinds of mistakes. It gives you a framework for thinking about other cases where high probabilities and large numbers interact in surprising ways. As the ideas continue to settle, there's a kind of beauty in the paradox's simplicity. It doesn't require advanced mathematics or specialized knowledge. It just requires clear thinking and a willingness to follow the logic wherever it leads. The setup is a lottery. The reasoning is basic probability. The conclusion is a gentle contradiction. And from that simple structure emerges a rich philosophical problem that has occupied some of the best minds in epistemology and decision theory. The paradox also connects to broader themes about how we live with uncertainty. Life doesn't offer many guarantees. Most of what we believe is based on incomplete information, probabilistic evidence, educated guesses. We make the best judgments we can with the information we have, and we move forward. The lottery paradox suggests that this is not just a practical necessity, but also a conceptual challenge. Even in ideal cases where the probabilities are clear and the logic is clean, there are still puzzles about how belief and probability fit together. This isn't cause for despair. It's just the nature of the territory. Uncertainty is woven into the fabric of the world, and our minds have evolved to navigate that uncertainty with remarkable skill. We're not perfect probabilistic reasoners, far from it, but we're good enough. We get by. We make predictions, form beliefs, take actions, and most of the time, things work out reasonably well. The lottery paradox is a reminder that even our best reasoning has limits, but it's also a testament to the fact that we can think carefully about those limits and understand them. In the stillness of contemplation, the paradox becomes less like a problem to be solved and more like a landscape to be explored. You can wander through its implications, considering different perspectives, trying out different responses, seeing what feels right and what doesn't. There's no rush, there's no pressure. It's an intellectual exercise, a form of mental leisure, a way of engaging with ideas for their own sake. And there's something deeply restful about that kind of engagement. It's not goal-oriented, it's not competitive. It's just you and an idea, turning it over, examining it, appreciating its nuances. The paradox doesn't judge you. It doesn't demand anything from you. It just offers itself up for consideration, and you can take from it what you will. As your mind begins to quiet, as the thoughts become slower and softer, the paradox fades into the background, leaving behind a residue of insight. You understand a little more about probability, about belief, about the gap between the two. You've travelled through a landscape of ideas, encountering familiar concepts in an unfamiliar context, and you've emerged with a slightly different perspective. That's the gift of a good paradox. It changes how you see things, gently and without fanfare. The lottery paradox will still be there tomorrow, and the day after that, and years from now. It's not going anywhere. Philosophers will continue to debate it, propose solutions, refine their theories, and you, if you wish, can return to it whenever you like, bringing new thoughts and new questions. It's a durable puzzle, one that rewards repeated engagement. But for now, in this moment, it's enough to have spent time with it, to have followed its reasoning, to have appreciated its elegance. The lottery tickets, with their precise probabilities and their stubborn refusal to all lose at once, have done their work. They've illustrated something subtle about how confidence and certainty differ, about how individual judgments and collective judgments can come apart, about how rational thinking navigates the space between the probable and the certain. And in that illustration, there's a kind of peace, the peace of understanding, however partial, the peace of engaging with difficult questions without needing immediate answers, the peace of recognizing that the world is complex, that our tools for understanding it are imperfect, and that this is okay. We do the best we can. We think carefully. We remain humble about our conclusions, and we keep exploring, keep questioning, keep thinking. The tickets rest quietly in their lottery, each one almost certain to lose, collectively certain that one will win. The paradox rests quietly in the structure of that situation, waiting to be discovered by anyone who thinks through the implications carefully. And you rest quietly as well, your mind having wandered through probability and belief, logic and language, individual confidence and collective impossibility. The journey has been gentle, the insight subtle, the conclusion open-ended, and that's exactly as it should be. In the soft darkness, as sleep begins to approach, the details of the paradox become less important than the experience of having thought about it. The specific tickets, the exact probabilities, the various solutions, all of these fade into a general sense of having engaged with something interesting and worthwhile. What remains is a feeling of intellectual contentment, the satisfaction of having spent time with a good idea, the quiet pleasure of philosophical contemplation. The lottery paradox, like all good paradoxes, doesn't really end. It circles back on itself, inviting you to think again, to reconsider, to explore from a different angle. But for now, the circle can rest, the thinking can pause. The mind can settle into a comfortable quietness, carrying with it a faint echo of lottery tickets and probabilities, of beliefs that seem rational individually, but impossible collectively, of the subtle gap between almost certain and certain. And in that quietness, there's room for sleep to arrive gently and naturally, bringing with it the rest that follows genuine intellectual engagement. The paradox has done its work. It has occupied the mind, provided something to think about, offered a puzzle worthy of attention. Now it can recede, leaving behind only a soft residual awareness that the world of ideas is vast and full of interesting corners, and that exploring those corners is one of the quiet joys of being human. The lottery tickets sit in their orderly arrangement, 1 through 1 million, each almost certain to lose, one certain to win. The paradox sits in its structure, elegant and persistent, showing where our intuitions about belief and probability come apart. And you sit in this moment of transition between waking thought and sleep, having travelled through the paradox's landscape, having appreciated its contours, ready now to let it go and drift into the restful darkness, where paradoxes dissolve and the mind can simply be. The next story is about to begin. Please relax and enjoy.